Good morning, good afternoon, and good evening, everyone. And thank you for joining us on our webinar titled Improving Animal Translation, Welfare, and Operational Efficiency with Appropriate Housing and Infrastructure Design. This is Liam Sanyo from Inside Scientific, and I'm very pleased to be your host for today's event. Today's webinar is sponsored by Technoplast and will feature Dr. John Hasenau, Principal Consultant at Lab Animal Consultants, and Jeffrey Zynda, Principal and Leader of Perkins & Will's Science and Technology Practice in Boston. Our speakers today will discuss practical options for housing and infrastructural design to sustainably improve animal welfare, data reporting, and reproducibility through the use of new technologies used by academia, pharma, and CROs to acquire animal activity data. And with that, I'm very pleased to introduce the first presenter, Dr. John Hasenau. John, thanks so much for joining us today, and feel free to take it away whenever you're ready.
Liam, thank you for that introduction, and good morning, good afternoon, good evening, depending on globally where you're at. With my talk, I want to go ahead and really focus in on the rodent housing needs from management and research point of views. And with that, I want to welcome the management groups. And in my past experiences, these are the bullet points that I would feel would be most important at this current time related to management needs. Increased density while maintaining footprint, the ability to have good tracking and monitoring of animals in near real time, promote animal welfare at all levels and maintain staff engagement, and keep costs contained and promote sustainability and operational efficiencies. And then also on the research side, the major bullet point that transitions is having translatable data, which may include repeatability and rigor. The other three bullet points are exactly the same as the management components, and they overlap quite well and complement each other. And I think that's very important in terms of the overall site visit and needs. My key objectives for you today will be how to improve the translational value of animal models through advanced housing systems, optimizing the animal welfare with advanced housing systems, how can locomotor activity serve as a digital biomarker, especially with infectious disease, and use of automated home housing systems to improve standardization of the cage and decrease human-associated factors of study disruptions. And then use of automated home systems to eliminate the shared instrument behavioral, physiological, and in general study disruptions that we can see when we're conducting studies. And as a segue into Jeff's component of the talk, why digitalization of a facility is now mandatory than elective from a design aspect. And most importantly, and hopefully from both of our talks, practical relevant information that you can use at your facilities. So getting off with the study reproducibility component, we really talk about then the replication through independent experiments, and we need rigorous and transparent experimental methods. And stages that impact this, especially with the housing component, is the experimental design, the methodology, and then the reporting aspects to both the journals and to others as to what was used during the study and how that was done. And I want to go into the ARRIVE guidelines here for a moment, because the original ARRIVE guidelines heavily emphasized housing and husbandry. Then in 2019, we saw that wasn't as much a focus in terms of the essentials, the top 10. And the reasoning for this, in my mind at least, is that these top 10, which were the sample size, the study design, inclusion, exclusion criteria, randomization, binding, outcome measures, the statistical methods had much greater impact on the study than just the housing alone. But since 2019, we've seen great elevations and interest in getting those contained and worked on. And now I think we've seen a resurgence of where housing and husbandry is critical as it has been in the past, and is actually maybe even more important now going forward. So with that in mind, I wanted to look at three different areas in terms of the current issues specific to housing and husbandry: macro, micro, and then study components in general. And focusing in on macro, we can see that the guide for the care and use of animals has mandated that we be monitoring in the macro environment temperature, humidity, light, airflow, and differential pressures. And we all do that well through our BAS systems, and then in other add-ons that may be part of our environment monitoring, we have secondary systems to check the BAS system. And even some groups have now gone to, if you see in the lower right-hand corner here, that little box, that is a box that can sit on top of the rack, as is shown in the far lower right corner. That is actually a rack environmental monitoring device. And that device can measure temperature, humidity, light, and motion and noise. And it correlates well then with what is happening actually in the room with individuals, staff, and or researchers who might be in front of the rack, and can correlate then with the measurement of the activity in the animal cage and figure out if there's any issues that way, especially in the evening hours when we have many different people coming into the room and doing things that way. In the microenvironmental area, I wanted to emphasize that we really need to look at the microenvironment in regards to the mouse. And the mouse at the mouse level is usually at the nose level, as been defined in earlier documents. And we're really looking at temperatures, humidity, airflows, lighting, noise, substrates that are being used in the cage, as well as husbandry items such as what is the nutrition, water, and cage housing items, environmental enrichment. But then animal handling has been a greater focus, and we'll talk more about that later on in this presentation as to how that has been changing here most recently. These are not as well regulated, and often these are averages through the rack. And better ways of looking at this need to be still defined and to be done. And that is being worked on currently with many of the manufacturers. The influence of the cage environment on rodent physiology and behavior has been nothing new. We've seen this for actually a couple of decades in the literature. In this more recent publication, 2015, by colleague Linda Toth, summarized many of these areas quite well, but there was a good focus on rodent housing varieties and where we have been and where we're going. And we have many different types. And these types are not just globally, but they're also within institutions. Many times, depending on our finances and ability to go ahead and get new types of housing units in, we do have quite a variety within the housing, within the institutions. And these can then affect different ways and different types of outcomes for our studies. And this is something that we need to keep in mind at all points. The ARRIVE guidelines points that out and wants us to define what is being used in terms of some of the housing situations, and also prepare guidelines that I didn't mention yet, but are there as well, would define that as well. Where we are now with the IBCs is very important in terms of where air is supplied, at what rates, positive or negative to the room, and other aspects of that with the IBC caging. Just as a historical perspective, pictorially, I wanted to go through what the different types of housings we've seen. The open caging was actually very early on, and we've gone to micro-isolators because of health status of the animals. And we continue with with IBCs because of the health issues with the micro-isolators and the inability to really maintain the microenvironment well in those situations. So the current standard is IBCs. And what we've seen with IBCs is different types of way to supply the air. The blower units are essential and or using the room air supply. But different types of blower units exist, those that are on the floors, those that are integral to the rack. And there are differences between these in terms of noise, temperature, heat, and other aspects with that. And that's important for the publications to be listing which ways we're doing this related to then the outcomes of the data. We are now seeing a transition due to the management aspects that I've mentioned earlier about more housing density, in keeping it in the same footprint. And the high density housing is providing then greater amounts of housing units in the same space, 80 versus the 96 versus the 80 that had been there, and 192 versus the 60 that had been there. And the other thing that is being done with some of the designs for the caging is having integral lid components with the bottoms. And this is very critical and innovative, related to then having greater space in the changing areas for the use of the housing systems, to allow then other space being utilized that way, and ergonomics with this as well. This is a great innovative design. Other things that we're seeing with the innovative designs is where the environmental enrichment is actually added into the cage, as you can see by this elevation in the lower right-hand corner of the cage bottom, allowing then animals that aspect of environmental enrichment in relationship to that, and being able to utilize that within their home housing unit. We also need to talk a lot about the automated home housing systems. These automated home housing systems have different technology base, and the technology base really started with video. They included then infrared, sensor plate, RFID, nose pokes, and most currently electrode capacitance perturbations. And these electrode capacitance perturbations are being seen here in the lower right-hand corner. And I want to emphasize that in the home housing systems, we're really talking about leaving the animals in their home house, their home cage, and not moving the animals out. In the upper left part of these pictures here, you see where these animals are actually having to be moved into these units, whereas in the lower right, we see where they are maintained in their actual home house, and also in the upper right picture as well. And there are many different varieties of these going on. I wanted to focus in on what's called the DVC. These have these capacitors that I mentioned earlier. There are 12 proprietary capacitors that are embedded in a plate underneath the cage. And what happens is you end up with a low frequency energy EMF, ELF, that is impacted by then the animals or the bedding, and it changes the signal. I want to emphasize that the EMF or ELF that is given off here is much lower than what we are exposed to. And the manufacturers, Technoplast, who have done this, have also run studies on both pathophysiology, physiology, and behavior, and seen no differences from this type of technology being employed in the cage. And they have papers on that if you do want to see those. The system as it works, you can see here on the video that as the animals are moving on our left, there is a correspondence to the signal on the right where it is diminished, related to when the animal is in that particular area and moving around. And that is the principle of this whole technology. And there are algorithms that have been developed then, proprietary algorithms related to this, not only for the animal movement, but if we talk about other areas, we can see here too, we can also see that if the bedding is implied or impacted as well, that will also be a decreased signal with that. And this is just showing then how that signal is decreased. And we have anomalies with animal activity that can be looked at, bedding condition analysis, and then on a different infrared capability on the cage itself or on the housing unit itself, you have food availability and water availability. Water flooding detection is something that I'll cover a little later in this presentation and how that's done. And no activity from registered cages or activity from unregistered cages. So these are all management components that have been built into the system and are quite beneficial to the users in relationship to that. We talked about the colors earlier, the going and changing diurnal rhythms by having different lighting in the middle of their dark or light cycle can cause issues for these animals. So some of the manufacturers have gone to either rack coloration and lack of disturbance then of the different lighting times, or to the cage itself. In the lower right-hand corner, you can see that is a total amber cage, and in that amber cage, embedded underneath the top of the cage, is a light source, and that light source is good for at least 2 weeks and can be changed to different diurnal variations on that. So this is a way that Technoplast has addressed this, and the advantage of this is that you can have cages side by side with different types of diurnal variations in relationship to that, and it's a very effective method in relationship. The talking about IVCs and then putting them out into the public domain and the academic domain and knowing which type of IVC you're dealing with is not a new concern. There are many different types of IVCs that we talk about. Again, they have different ways of supplying air, different ways of going ahead and working, and it's important that we know that. Doctors Lipman and Perkins have thought about this and have published in relationship 5 areas of what should be published minimally for IVC definition. And there should be a talk of this at the workshop at the National ALAS meeting coming up, a panel discussion that will be describing this and talking about this in more detail. The air supply, if we look at that as a part of this IVC definition, we can see that there can be different effects with the air supply in relation to behavior aspects. And this is a study that had been published and done where the air supplied either at the floor bottom or at the top of the cage. If supplied at the floor bottom, the animals tended to be more anxious and created behavioral issues related to that. Whereas at the top of the cage, it was not as problematic or a concern. So again, this is something that should be published and should be well defined, as we talked about earlier with our publications. Handling of animals, as I alluded to, I want to give Jane Hurst a shout out from the European side here, where she really promoted and pushed this there, and now we're seeing this movement here in the U.S. And tube movement, properly trained, performed in high anxiety animals and moving animals that way. I'm also been alerted to and just reviewed a paper from our Canadian colleagues who are looking at just a handling system, a 3-day handling system for acclimation of animals. And what it boils down to in all of this is getting the animals acclimated early on in the study will give much better data and results at the end of the study. So this is where really, if you do have to handle the animals and do manipulations of them, acclimation is a critical viewpoint, and doing that well will yield better data results at the end. That report out of Canada should be coming in the near future here that we're talking about. And then handling of animals, in addition to just what we're doing when we're actually handling them, who is handling them is as important as well, and the amount of time that they're handling them. And this is a good paper that indicated that there could be differences in the genders of staff handling them, both from the research and from the research and care side. And this can then cause data differences in relationship to that way. So having that documented in terms of who is doing it and frequency is important as well. Cage changing and animal movements, the use of the need to cage change and looking at what that does cause in animal movement related to natural and normal type of behavior patterns. We can see range of impacts are from 48 to 96 hours post-changing, and that depends a little bit on room size, procedure, sex, strain, and time of the day of cage changing, but primary aspects are seen during the daytime activities, and age-dependent changes were not really seen in relationship to this. A multicentric study was done in relation to that on the C57 BALPC mice, and looking at this with the DVC system, as I mentioned, but this was backed up again with a biome system that was used as well. And conclusions were similar in terms of the amounts of disruptions and differences that were seen in behaviors post-cage changing on these animals from the home cage. So looking at this from a heat map point of view, we can see that, again, these are nocturnal animals. Our greatest activity is in the night. The lack of activity during the day can be then disrupted via bedding change, as you can see here, or mice weighing. Bedding change having, of course, a greater impact in relationship to that. If we look at this from that multicentric study, we can see that there was commonalities in the patterns across the globe in relationship to that. So this is a very good indication that these are similar that way. But you can also see that there are differences at each institution in relationship to the amount of activity and the amount of disruption in those activities from the daytime activities with that as well. So there are individual differences at institutions, but globally the patterns are very similar, and we have very good correlation in relationship to that. The continuous home cage monitoring as a tool allows behavioral and physiological monitoring of the animals, minimum or no human intervention or bias, depending on how much intervention you need for study conductance. It increases the understanding of the normal diurnal behaviors and activities. It explores how environmental manipulations interact with genetics and age. And it helps you understand and us understand the magnitude and duration of procedure effects. And we can increase the study reproducibility with this as well, that would then add to greater translatability, hopefully, in this. One of the examples I wanted to do here is talk about night welfare checks. What is being done with the automated home cage system that I'm talking about with DVC is the evening of the evening of the day before is being compared to other evenings. And what we're looking at is then doing a comparison of what is happening that morning. So we have a morning report that would come out at like 6 a.m. and staff may be coming in at 7 or 8. And they're able to go ahead and actually look then at what may be alternate behaviors compared to previous activities from either the day before or the week before on an average. And with that, you can see that in this particular example, there is a drop in what we call the bedding status index, which again is looking at the algorithm for the bedding status. And there's a huge drop there in signal, but in correlation to that, there is a drop in activity as well. And that drop in activity indicates then that we've had a flooding problem, water flooding effect, either from auto watering or from a water bottle issue. And that would be immediately reported then via email to the management staff, where this can then be corrected and taken care of. So what we do see with this when this does occur is we would need to change the cage. And when we change the cage, there is not an immediate type of result in terms of behavior. This behavior then is prolonged in terms of what has happened here from the cage change, as we talked about before, and 1.5 day impact minimal in relationship to normal behavior being redeveloped here again and normal activity within the cage. So this is important. I want to now transition into infectious disease studies and talk about our current status in terms of the COVID-19 issues, the pandemic that we're going through. The mouse models that we have for that have the receptor for the COVID-2, the SARS-CoV-2. And with this, we see that much research has been done in relationship to this. And the research has focused on then in the mouse models, looking at body weight issues and the decrease in body weight in terms of infectious component. But also in this, we can see that there is an impact on activity. And interestingly, the activity precedes, the inactivity precedes the weight loss. And it may be a better bioindicator and biomarker for this these studies. And going forward, this is a way to go ahead and more accurately predict what might be impacts in relationship to the SARS-CoV-2 mouse models for this overall. So it's important, again, that this activity is decreased and then the weight changes follow overall. Biocontainment studies are not new, and we've been using hermetically sealed housing systems, something called ISO systems. There are both ISO negative and ISO positive, and obviously with infectious disease, you'd want to use ISO negative systems to maintain that infectious component inside the cage. And these are hermetically sealed again, so they're very safe to use. But early on, these cages have been used for the Middle East Respiratory Syndrome coronavirus, the preceder of our current issue here back in the 2000s. And we've also seen this used in Napa virus issues, as well as bacterial issues with Burkholderia, and then also Zika virus issues in regards to that. So what has happened at Technoplast is they've gone ahead and added on to their ISO caging the DVC component to be able to go ahead and look at activity levels from the home cage in relationship to these studies, these biocontainment studies. This has got both facility management and research aspect components that are very positive for the studies. On the facility management side, we see that we can have better animal welfare checks relationship to that. Also looking at the bedding component with the algorithms there and not having to look at changing the bedding on a actual calendar basis, but more on a need basis. And flooding detection can be done as well. On the research side, locomotor activity, high throughput data, standardizing metrics, and reducing bias in regards to some of the activity levels there and the movement levels overall. So really, this is enhancing biosafety in this particular situation for the ISO caging and reducing the animal and cage handling in relationship to that. If we look at this from the high density caging situation, and this is something that Technoplast is working forward on, is to go ahead and put DVC into the high density housing emerald line that they have. The same opportunities are there for both the management and the research side that we've just mentioned. And again, in this situation, we're seeing more of an enhancement and a focus on animal welfare and not so much on the biosafety component, but there is a biosafety component as well with less bedding change for the staff in relationship then to allergy issues that might be occurring from that. So in all of this, I want to thank everyone for being here, and I hope we've given you a few nuggets for going ahead and to learn from this. And with that, I want to turn this over to Liam, who will then pass this on to Jeff. And thank you again for being here.
And with that, I'd like to turn things over to Jeff Zynda. Jeff, thanks so much for joining us today, and the floor is yours.
Thanks, Liam. I'm going to take a little bit of a different tact on talking about digitalization in the vivarium because I am not a scientist, but rather I am an architect. So we're going to talk about the built environment today. So after a brief introduction, we're going to focus in on the areas of facility optimization, opportunities for energy reduction and carbon footprint reduction. And really, when we're talking about digital integration in the vivarium, what are some of the design considerations we need to take into account? So I like by starting, where John had underscored, what is the purpose of digitalization, or how can we apply that to the vivarium environment? And I really love this quote from the ILR guide that says, the role of a vivarium implied here is to uphold the scientific rigor and integrity of biomedical research. And so how can digitalization really be a foundational element of upholding that mission? And so today we're going to look through the three different lenses in the digital vivarium. We're going to look at energy efficiency, opportunities to optimize labor, and impacts on physical design and the design process itself. So first, we're going to take a look at facility optimization. And so The challenge that was posed to us was to inquire, can the use of digital monitoring of home cages optimize change rates and in turn potentially reduce the amount of space allocated to support elements such as cage wash operations in terms of both first capital cost and ongoing operational cost. So the facility that we took a look at here is about a 20,000 square foot facility. It houses about 8,000 cages of mice, about 1,500 tanks of zebrafish, and then a small number of rabbit cages. And over on the right-hand side of the screen here, you'll note in this purple area as outlined in the dashed element is based on standard planning metrics what a wash facility might incorporate or encompass. And so this 8,000 cage facility would have required a weekly full cage wash or 1,600 cages per day. So in terms of a square footage allocation, about 650 square feet of the facility would be dedicated to soil side operations. About 550 square feet would be dedicated to the clean side for a total of about 1,200 square feet of space based on standard cage change metrics. And so in this particular location for this facility, about 1,200 square feet of space equated to at $1,400 a square foot was just under 1.7 million US dollars. Not an insignificant investment for both the physical environment as well as the equipment in this space. And so in order to test this theory of facility optimization, can less space be used? 3 target housing rooms with a capacity of just under 500 cages were set up for a 6-month study. And after monitoring the first 2 months, the study was changed because very minimal amounts, as you can see in the columns in month 1 and 2, minimal amounts of changes were needed. So on a weekly basis based on home cage monitoring. And so that was switched from 1 to 2 weeks. And as you can see, as the percentages increase over the remainder of the study going to month 6, that the percentage of reduction of change frequency varied from about 43 to 56%. And so, it was determined in this study that essentially through the use of home cage monitoring and really looking at the status of soiled caging and only changing those cages when needed, not on a scheduled or routine basis, that the amount of cage changes could be reduced by about 50%. Very significant reduction. And so then when we back out and look at what is the impact on the built environment, that 1,200 square feet can be reduced down to about 840 square feet, or a reduction of a third. And at those dollars per square foot we were looking at before, that brings the facility cost down for this portion to about $1.2 million, or a savings of about of $500,000. Not insignificant for a facility of this size. So taking a look at the second category we wanted to look at here is energy use reduction. Obviously, Vivaria are in energy use intense types of facilities, one of the most demanding in terms of utilities. And so the challenge we had on this study was to take a look at real-time digital monitoring of air quality and conditions, and can reducing the conditioned air supply while not compromising safety and repeatability of research baseline conditions, could that result in significant savings? And so just to frame this a little bit here, we reference 2 different criteria that are commonly adopted around the world. First being air change rates in the ILAR guide, which at around 6 air changes per hour at a 10-foot ceiling, 1 CFM a square foot, about 10 to 15 fresh air changes per hour in housing is pretty normative. More adopted throughout Europe, the Philosophy Euro Guide, and as adopted in ETS 123, looks at a little bit higher air change rate of about 15 to 20 air changes per hour. Now we're talking about the macro environment here, not the microenvironment that John focused on earlier today, but the room and the housing rooms that many of these cage systems go into. And so when we start to think about the energy profile of a vivarium, this chart here gives you an idea based on electrical load, the plug loads, lighting, where are the different areas of focus. And I really want to call your attention to really the blue regions where we look at the conditioning, either heating or cooling, and movement of air, because that makes up over 60% of the energy budget of the average vivarium. It's very significant. So conditioning that air and moving it around, supplying it and exhausting it is the major intensity of energy use within the vivarium, as many of you well know. And so we looked at the theoretical application of demand-controlled ventilation, or DCV. And these are systems that go by a lot of different trade names, but in general, what they do are they're sensor-calibrated sets that look at the quality of indoor air in terms of total volatile organic chemicals, TVOCs, airborne particulate, and ammonia. And they monitor for air quality and can reduce air change delivery or reduce air change rates based on those quality parameters that are input. So maintaining a safe operation. And so this next couple slides here it was a study of 100,000 square foot vivarium for 100,000 hours, went on for a number of years, is actually continuing, and looking at the percentage of time over acceptable thresholds in terms of parts per million of TVOC for, in this facility, non-human primate open caging, ventilated cages in rodents, and also open caging. And then looked at, again, the contamination of that air as related to background acceptability over time. And so the outcome of this study was that, continuous digital air monitoring of the quality of the air can result in significant reduction from 15 to 20 air changes per hour down to approximately 4 to 6 air changes per hour, while maintaining high quality and acceptable, from a regulatory perspective, conditions for the animals. And again, focusing on the macro environment, decoupled from the microenvironment. So the potential there for savings, as shown through this study set, was about 60 to 75% of the airside energy savings is attainable looking at demand-controlled ventilation systems. And this was recognized just about 2.5 years ago by CCAC, the Canadian Council on Animal Care, the first standard that we're aware of that had recognized and published acceptable norms or acceptable standards for air quality. They published an addendum, as I mentioned, that establishes parts per million thresholds and acceptable maximal values for common air quality indicators in vivaria, being ammonia, carbon dioxide, airborne particulate, and total volatile organic compounds or chemicals, TVOCs. And so this was a significant breakthrough through the industry, because now there's a reference standard that's supported by government regulation in Canada that is now being looked at being adopted in other jurisdictions as well. So the last category we're going to look at is the potential impact on labor optimization, and looking at another study of how a facility could perhaps deviate from the norms and metrics that had been established in the past through the usage of home cage monitoring, and impact positively the amount of labor required for movement as well as wash operations. And so the challenge here is, could labor be optimized through home cage monitoring and the introduction of automation in wash operations, so that staff weren't doing more of the menial labor, if you will, in wash and support, but really focusing in on animal health and welfare and the research support. And so a 4-month study of around 600 cages was showing that about 40 to 50% of the cages did not need to be changed at their normal 2-week interval, 14 days. And this was validated via digital monitoring. And so the theory there was that labor could be reconsidered, as I just mentioned. And so here's a diagram of this facility here, showing the housing units for rodents up on the top of the screen. And in the lower portion, so the lower portion, the wash facilities and wash operations associated here. So of a total 10,000 cage facility, the weekly wash schedule was about 2,000 cages per day was required. And here outlined on the lower right-hand side of the screen is the soiled and clean operations to perform that washing. And so in order to accomplish that, originally, when we studied this facility, an existing facility, on the soiled side operations took about 5 people to move through all the different processes, 5 full-time equivalents, working at 3 tunnel washers and 1 cage and rack washer in order to process the anticipated load. And then on the clean side of the operation, there were about 8 people in order to take that clean caging, either autoclave or sterilize that and return the cages for feed and bedding before they could be returned back to their housing units. And so quite a labor-intensive process. So again, after we took a look at the reduced wash throughput and came back to that 600 cages per day that was now needed based on the optimized schedule, based on home cage monitoring, and started to couple this with the ability of adding automation along a tunnel line, the soiled side operations could be significantly reduced by about 3 FTEs, and the clean side operations by about 5 FTEs. So not insignificant. So, as the cage changes occurred in a range of 18 to 24 days and resulted in the retasking of 4 people for cage change and movement. Again, not insignificant. And then in total, the wash-related labor reductions allowed for the retasking of 8 people for both soiled and clean side operations. And again, this is a significant amount of resource and effort that could be not eliminated, but rather retasked so that better research and better research outcomes could be achieved. And so when we start to think about what do we really need to do to integrate some of these technologies into the digital vivarium, what are the design considerations? Well, just taking a prototypical non-densified room, here's about a 240 square foot or 22 square meter room that could house about 460 to 480 cages in single-sided racks along with their blower units. And when we start to think about some of the design considerations, as John mentioned, there's a wide variety of technologies out there that use from video technology to infrared to ELF and EMF types of technologies to monitor caging. And it's critically important that up front you understand the impacts or how these systems work and the impacts on the infrastructure of your facility. And so what critically do we really want to be looking at? A lot of this ties back to data, where we have to locate server rooms. Are we looking at hardwired or Ethernet-based systems, or are we looking at wireless technologies in order to gather that data that's critical to report back to all of you? And so when we start to think about hardwired systems and the ability of data transfer, there are a variety of adopted standards, whether it's in new facilities or facilities yet to be constructed, looking at categories of maximum data rate from Cat 3 to Cat 6A. And you can see in the chart here that there's quite a wide variety of data transfer from 10 megabits per second to 10 gigabits per second at different frequencies. But the really key thing in facility design we need to look at is what is the maximal run in typical distance before we can run from a point of use to where an information data frame or a server rack might need to be located. And so, prototypically, we have long spans in these buildings. Typical vivarium structural bay is about 10 meters or about 3 holding rooms wide or housing rooms wide. But every 40 meters in hardwired systems, we would need to have, following the most lenient rates, an information data frame or a server room. These are prototypically spaces that don't occur within Vivaria because they're hard to service in those biosecure environments. And so this has a real impact on the layout and planning of vivarium facilities if you're looking at the necessity of hardwired approaches. So the other approach is looking at wireless technology and wireless access points. And these can easily be located in housing rooms but they also have their challenges as well. And so when we look at wireless access points and the different commonly accepted global protocols from 802.11b to 802.11ac, you'll see that there are theoretical data transfer rates that range from about 11 to 1300 megabits per second. But then there's the reality of data transfer. I think if everyone has learned, if anyone's learned anything over the past year, probably being on video conferences like ourselves on a daily basis, is that the real world interferes with data transfer and especially impacts video quality and high transfer rates. And so an environment that is incredibly dense in terms of metal and interferences, like a vivarium with intervening partitions, lots of distributed ductwork, controls, things of that nature, actual data rates from the theoretical maximum start to drop significantly. So to put this in context, gigabit speed really is around 125 megabytes per second. And comparing and contrasting some of the technologies for home cage monitoring out there, a standard resolution 720p video feed requires about 25 megabits per second, or 7 gigabytes an hour. So you need to look at the throughput needed for your system to plan whether you need hardwired or if you need wireless or support in terms of infrastructure. Another thing that we traditionally haven't started to look at until home cage monitoring became as prevalent as it is today is the impact of RF and EMF on wireless transfer. And this is just a map of a facility showing from an electric room and even electric panels the amount of electromagnetic radiation that's given off that can significantly impact wireless data transfer. So this is another design consideration that we really need to be looking at in the digital era. So just really briefly to wrap up and look at the application of this here, a theoretical study for a major pharmaceutical company looking at a significant vivarium with automated cage wash that was built in the era just before digital home cage monitoring became prevalent on the open market. And they were looking to optimize their facility and improve research outcomes by reducing labor and energy expenses. And so looking at the existing layout, there were some physical limitations between where you see the 40-meter section of where the vivarium is to where the closest data frame was outlined. And this would have been in excess of what is allowable in terms of a run distance for hardwired data cabling. So it would have required the installation of 2 additional data rooms, and this would then have to compromise research space that was already assigned. So that was deemed unacceptable. So the solution there then became putting regularly spaced wireless access points, really starting to look at some of the technologies and integrating, making a decision on the home cage monitoring technology that worked in concert with the physical constraints of the facility in order to come up with a workable solution. So if I can emphasize anything, it's early decisions on these types of home cage monitoring systems has a significant impact on the infrastructure of building, whether for new build or for retrofit. So in summary, just 4 points that hopefully you can take away today and positively influence your situations, your facilities. First, there's a huge amount of potential to migrate away from traditional laboratory planning metrics, and especially for wash operations, and really impact your first capital or renovation costs, as well as ongoing operational costs of these facilities through the use of digital home cage monitoring. Secondly, as hopefully we illustrated, digital environmental monitoring can have significant impacts on the amount of energy expended in your vivarium. Thirdly, the use of digital monitoring in conjunction with automation is kind of a twofer, and it can really, not only impact the amount of energy in the facility used, but also significantly reduce the amount of labor associated with the movement and washing of caging. And again, as I said before, and I can't emphasize this enough, No two systems are designed the same way. In terms of digital home cage monitoring, it takes various forms, really understand how they work, and what infrastructure is going to be required to support them, so that they are easily implemented into your facility, and you can start to take advantages of the operational cost reductions and labor reductions outlined above. So with that, I thank you very much for your time.
Fantastic. Thank you, Jeff, for the presentation. So the first question, and John, I'm going to direct this one to you. What other kinds of experiments could you imagine doing with the DVC, both within and outside your research area?
Thanks, Liam. So I presented on infectious disease, but we can also be using this system for many other areas, such as cancer research, any of the behavioral type components. There are studies that Technoplast has been putting into their archives, and they can be reviewed by some of the participants in regards to that. But it's really quite versatile and very open. And the main thing here is activity, and looking at cage activity, group activity in regards to this, and how the animals are affected with the activity levels overall. So it's very applicable across many different areas of science with that.
Excellent. Thanks a lot, John. Here's a good question for Jeff. What's the impact of high density housing in older existing animal facilities that often already experience issues with maintaining an appropriate temperature or humidity level during the winter? What would you suggest for these cases?
That's a really good question, and it's going to be one of the prototypical answers of it depends. But realistically, the impact of high density housing is comparing and contrasting the macro environment to the micro environment again, and looking at how some of the better designed high density systems that are out there can also mitigate temperature and humidity at the blower level or the rack level. So there are ways, even though your macro level facility may be struggling for one reason or another as a facility ages, there's ways to offset that through the proper selection of the densified caging. So in concert with one another, we have run into very few situations where you can't overcome some of those failings. Now, obviously, that's related to the order of magnitude of what the difference might be. But really look towards some of those systems that can provide, microenvironmental control of the environmental parameters, because that's really what counts, not so much the people spaces or the macro environment.
Excellent. Thanks a lot, Jeff. I think, John, do you have anything to add to that?
I was just going to add in that, Jeff, some of the newer blower units actually have control for both humidity and temperatures on them that can help with that then at the rack level. So, and I think you covered that. So excellent response, Jeff.
Fantastic. Agreed. And Jeff, I think I'll direct this next one to you. How do you handle the heat load of a room if you reduce the air changes per hour?
Again, a very good question. So there is a certain amount of rejected heat into a space, but as we look at improved technology, especially with advanced motors, ECM technology, and things of that nature, the amount of rejected heat into a space is relatively little. And as long as we're hitting those baseline maintenance measures, then reducing heat loads is very achievable. What we have seen is as we're reducing the amount of heat load or the amount of air change rates in spaces, the direct connection of exhaust, perhaps supplying air from a room into a blower unit, but then directly connecting that exhaust so the rejected heat isn't going into the room, but rather channeled into an extract, has become more prevalent over time. So that's one strategy that has become increasingly popular as that shift is occurring.
Fantastic, great answer. And John, I think I'll direct this next question to you. With the decreased need to perform cage changes, how does this impact health monitoring? For example, does less frequent handling of the animals, have you observed changes in their health?
The ability for the systems to look at night when the highest activity is has then good correlations with what the animal's health is, and actually has better prognostic ability than what we have been able to do at the human level, going ahead and looking at cages on a daily basis, which may only be a 1 or 2 second observation related to resource, and be able to predict that health of the animal that way. So actually, I think it's a better prognostic indicator, and it augments what we still do in the room during the day. So yeah, that's basically it.
Yeah, that makes a lot of sense. Great point. Next question here, and Jeff, maybe this one's for you. What wireless standards are currently being used, and are they affected by things like NMR or MRI units?
So I guess I could read that two ways. Using wireless access in MR or high radio frequency interference environments is always difficult because of the amount of interference produced in those spaces. So we tend to see shielded data cable being more predominant, hardwired connections. Now, however, the current standards for 802.11 AC is really the most advanced, if you will. It's the most highest throughput, most recently adopted international standard. Because of the frequency range that operates at, it mitigates to a certain degree high fields. It is better, but it is not flawless. So really long story short, in high interference zones, looking towards non-wireless technologies where possible is advisable. And that might mean, kind of daisy chaining or linking wireless access points to hardwired service connections in those higher interference areas, but being free to distribute access points in non-interference areas in other parts of a facility. I hope that answers your question. It's a topic we could spend a lot of time on, but good question.
Yeah, I'm sure. Fantastic. Well, great answer. And I think in the interest of time, we'll maybe squeeze one last question in. Here is a good question. John, can you house rats in the DVC, or could you house maybe a single rack with multiple species of rodents like a mouse, rat, or a hamster?
So that's really a question more for Technoplast in terms of where they're developing some of the DVC technologies. But my understanding is they are moving toward going ahead and adapting that into the rat caging as well. And of course, you can go ahead and house different species in different cages as long as they're isolated enough from each other. That way, you would have to have your ICOOK approve that, of course. And that is usually obtainable related to how the airflow situations and designs of the racks are for that. So that is achievable and can be done.
Fantastic. Well, thanks so much, John, and also Jeff, for your really fantastic insights, both in the Q&A today, as well as in your great presentations.
Thank you. Appreciate everyone being here.
Much.
Yes, definitely. Thanks, everyone, for participating in the webinar today. And last but certainly not least, we'd also like to thank the sponsor, Technoplast. So in closing, thanks again for taking part in this Inside Scientific webinar, and we look forward to having you with us again soon. Have a great day, everyone.